And that's really what this module is intended to be about. And that's why it's called critical thinking. And that's why you probably noticed there are two of us. On occasion we get lecturers in as observers, but in this case the idea is that a lot of the lectures in this module will be done as double acts. Now I hope that this will work. As you can probably guess, it's a bit of an experiment. But one of the reasons, and I think it'll become apparent as we go through today's lecture, is that science is not about us telling you what is real. You're not, being a scientist is not just learning science, it's a whole set of professional practices, and a lot of that turns on doubt, on criticism, on thinking about what you were told. And for that reason, it particularly struck us that having a single authority at the front of the lecture room was undermining that very set of ideas. So there are two of us. So there are two voices in dialogue, and we will on occasions, I'm sure, disagree. And Jeffrey is still disagreeing to a degree now. Yes.
I only wanted to say that when we were planning this course, we had disagreements both about what should be in it and also about some of the things that are in it. So there are going to be disputes as we go along.
Yes, certainly I suspect that I know Jeffrey and I are going to do another lecture picking up on philosophy of science next week, and we don't have quite the same views there. I suspect that some is there. Anyone else? I mean, the other reason why there are two of us is that we do want, at least for parts of these lectures, there to be dialogue, so do feel free to ask questions along the way, and that's one of the reasons why we're sort of asking for your comments, your views now. And we'll be doing that at other points in today's lecture as well. So it's not intended to just be us telling you stuff.
This is the first of a number of scientists that we're going to be looking at in the lecture today. And this man, who's always called in the West Alhazen, is quite an important figure because he stands between, if you like, the ancient world and the modern world. Islam came to power all over the Middle East in the 7th century and afterwards, in areas that had been occupied by Greeks. And you've all heard about Greek science, you've all heard names like Euclid, Plato, Ptolemy. You might not know what they did. These are names that are almost household names. And Muslims are very interested in what the Greeks have said. Sometimes 500 BC, sometimes 200 AD. Greek tradition is very old. And now here are these Muslim scholars in areas that were once inhabited by Greeks, reading what Greeks have said about science. And one of the things the Greeks have been very interested in is light and in vision. And it must be said that a lot of what they thought about vision was completely mistaken. But the fact is that even mistaken ideas, when they're discussed by people who are determined to solve a problem, can be productive. And so Alhazen looked at some of these mistaken Greek ideas and came to a new idea, a new theory about vision, which actually influenced certainly Western thinking for several hundred years. What did the Greeks think about vision? They had at least 4 ideas, and I'm not going to go into all of them in detail, but the most famous one is that light comes out of the eye and falls onto an object. The Greeks, some of them, thought that the reason we can see things is that the light itself comes from the eye and falls onto the table. Now, we don't believe that today, but it was once a very influential idea. They had this idea because they said, well, vision must be like the other senses. You know, I touch things with my fingers, so maybe the eye is like that. Maybe the eye touches things with light. Another idea they had was that objects themselves send light, or send objects into our eyes. They thought that perhaps little replicas of objects streamed away and entered our eyes. And this seems to us a silly idea now. You know, how would these little replicas get into our eye? But again, that was quite an influential idea at the time. Alhazen wanted to try and resolve all of this. And one observation he made was that if you had a row of lamps or candles and their light passed through a little gap or a slit, then you would see the same lamps on the wall behind. It's not important for this explanation that they're upside down, but that is in fact what you would see. And Alhazen did something very simple. He simply put an obstruction between this lamp and the wall, and he realised that one of these lamps had disappeared. That seems to us very obvious, and we wonder why no one else had noticed that before. But what it told Alhazen was that the light couldn't be coming out of his eye. It must be a property of these lamps themselves. So that in a way killed the Greek idea that light streams from the eye onto things outside. It also killed the Greek idea that light somehow blends. It must be travelling in a straight line, otherwise you wouldn't be able to cover up one lamp and remove the image of one lamp on the wall.
The other thing that is absolutely critical here is that Alhazen was one of the earlier people, certainly pretty much the earliest in the modern tradition, who decided, who thought that the right way to work out what was going on was not to think about it, but to do an experiment and see what happened. So you're seeing here, certainly in the modern scientific tradition, the beginnings of experimentation in the way we think about the world.
And that's an important point, because the Greeks, for all their cleverness, perhaps relied too much on reason. The Greeks were very good at imagining what the solution to a problem was, but they weren't great experimenters in the main. There were people like Archimedes who were, but the people who came up with these ideas were doing that for pure reason. And Alhazen also went on to argue that light must come from an object, it must travel in straight lines, and he thought the lens was the actual sensitive part of the eye. He was wrong about that. We now know it's the retina, but he believed that the lens was connected to the optic nerve. So although his idea about vision was mistaken, it was a very much better idea than the Greeks had come back with. Now, one question is, why didn't they just do a dissection and find out what was going on? And one answer to that has been that under Islam, human dissections were prohibited. This is an article which criticises that idea and says, actually, there doesn't seem to be any prohibition in any of the medieval literature. And moreover, that human dissections are actually quite common in the Islamic period. And if anyone's interested in looking this article up, there's some more information about it. But once again, dissection isn't something the ancient Greeks did very much of. As Stuart says, they were not experimenters, but it seems that in this period, people were more and more trying to find things out by observation and experiment. So Alhazen is a transitional figure in the history of science, because not only did he take the Greek tradition, criticise it, and improve it, but the book he wrote, which was translated into Latin in 1280, influenced Western thinking about vision and light the next certainly 400 or 500 years after that.
And this is an example of its influence. Not in science, but in art. Because at the top, what apparently you have is two versions, probably about 100 years apart, of essentially the same, show the same subject matter. You'll see that in the top one, everything is portrayed in a very flat way. This awareness, increasingly pervasive in Renaissance Europe, is starting to change the way people were doing art. Perhaps to a degree, changing the way they looked at things. So you can see that the first one I say is drawn flat, and in this artistic tradition, generally speaking, the size of things is shaped by their importance. You're getting here to the idea that because we know that light is travelling in straight lines, you can actually produce a construction and make things look as though they have a real depth. So it's changing certainly the way artists are looking at and recreating the world. And of course, optics is also having other effects as well. One of the people we saw in the film was Galileo. And obviously what we're seeing here is optics provide the basis for the first telescopes. And Galileo was starting to make use of this. This is actually also, and we'll come back to this as being one of the reasons why we feel that it's important to have a broader awareness of science as well. Because the sciences feed into one another. In this case, we have optics feeding into another branch of physics. We'll see other examples later which are different. So, Galileo is starting to make first astronomical observations by telescope. And so Galileo is a fairly little figure because of this. And oops, this was one of his early drawings. What this is Jupiter. What you can see if you use actually even a relatively small, a relatively normal pair of binoculars or a relatively small telescope, is not that Jupiter you'll see as a blob, and it's currently, if you look up about south, shortly after it gets dark, maybe 5 or 6 o'clock, you'll see a really bright star high towards the south. That's Jupiter. If you have a pair of binoculars at home or some such, I'd recommend you have a look at it. Because what you can see are these blobs to either side. These are the 4 largest of the moons of Jupiter, referred to as the Galilean moons for this reason. And what he saw was that they moved. And he worked out from that that the Jupiter system was like a little solar system with moons going around the centre of Jupiter. Now, this was before reasons will come to know. So this is actually a modern picture showing the same using a proper telescope, and just to show that you can get it with a relatively small telescope, this is actually taken in my backyard using a telescope at home. And you can see that the moons are in different places every time. The reason this was important is that at that time, the idea of the structure of the solar system was still the Ptolemaic one.
I think I can talk about that in some parts of Asia that idea was just like maybe up the window and no one needed it and really pleased with that light was going around the sun.
They will be right. I think it was an idea that would be going around. But certainly in Europe, we were still following the Ptolemaic system.
Actually, can I say something about that? Because you're right, the idea that the Earth was not the centre of the solar system had been around for some hundreds of years. But it seems that Copernicus, who we're going to talk about,
Not as such.
okay, but Copernicus was sometimes credited with being the first person to prove this in Europe, was actually the first person bold enough to do it. And it seems that other people had had the same idea and have even written a lecture about it. It's just that people were quite happy then with the idea that you could have 2 notions at the same time. It was perfectly, people didn't think it's schizophrenic to believe on the one hand that the sun is at the centre of the solar system, but on the other hand to tell people that the Earth is at the centre of the solar system. So it's quite right to say that these ideas have been around for centuries, but it's only really in the early modern period, around 1600, that people were anxious to say it's definitely this way and not that way. It seems that people could live with contradictions much more than we could before that time.
But as we're talking about, the pervasive idea was that the Earth was at the centre, and seeing this example of things that were clearly not going around the Earth, but going around Jupiter, was one of the things that substantially moved people towards the new idea, well, the rediscovery of an old idea, that in fact the sun was the centre of the solar system, so the Copernican model. And so again what we're seeing is observation coming over reason. So we're moving towards the idea that the way you learn about things is not by thinking about them, not by deduction, it's by observation, by experimentation. And this is something we'll be developing over the next quite substantially through this module, is that how to do this. Anything to add? Next slide. Okay, one of the early empiricists and philosophers, particularly articulating this, is Francis Bacon. Very much like this quotation. Men have sought to make a world from their own perceptions and to draw from their own minds all the material which they employ. If, instead of doing so, they consulted experience and observation, they would have the facts and not opinions to reason about, and might have ultimately arrived at the knowledge of the laws which govern the material world. Bacon is actually has been claimed to be a martyr to the experimental method. He died of pneumonia, which it's said he contracted while carrying out early experiments on refrigeration, burying peas in snow to see if it reduced the rate at which they spoil. Jeffrey's a skeptical.
There are modern martyrs to science who kind of swallow toxins and bacteria and things like that, so the traditions lie in that.
So, in the first part, then we need to go into some routine stuff, hand out handbooks and talk about how you're going to assess and so on. The reason why we're bringing this ideas in is that science is not just about knowing science. And the way I like to put this is we aren't about teaching you science, we're about making you into scientists. And so that is not just scientific knowledge, it's a whole set of scientific practices. And this is also one of the reasons why we give you so many lab sessions, because you have to be able to get out there and produce the observations and interpret those observations yourself. And that is one of the main things to this module. Anything to add to that?
I don't think so. Is there something you think I should add?
No, just. And so as we go into this sort of admin bit, I'll give you this quotation to think about, which I found a few weeks ago, which is, as an adolescent I aspired to lasting fame, I think natural certainty, and I thirsted for a meaningful vision of human life. So I went to a scientist who's like becoming an archbishop, so you and I'll leave that as something to think about. Well, as I say, we do need to do some housekeeping stuff, get out the module handbooks, and as we do that, we'll talk about what the assessment is going to be. We'll give a little bit of a demonstration of the practice you're going to be doing as well. Okay, so I'm going to need to pass around some signing in sheets. I believe I'll write all this today. Here I've got a aggregated document. Obviously there are going to be the lectures. We're also going to have 4 tutorials, and these are connecting into the ways they're going to be assessed, so these are going to be important. We're going to do them in a slightly different way to the other modules so far. Rather, they were real tutorials rather than small classes, and so they will be for each of the tutorial groups. We're going to divide into 2, and you'll get 1 hour each. So you'll be working harder for a shorter amount of time. We think that's a more useful use of the time. And we are going to be distributing the ones on SRS, the distribution on SRS. So don't go by SRS. We will put on Blackboard soon where and when you're going to go through tutorial groups. Okay, and there's also going to be 1 practical in there, which is going to fall during the GIS week. I'm afraid it's the only time we can get the labs for enough of it. And I'm sure it will. The assessments, I'm sure, will be more than a little interesting to you. And you need to pay attention to this because there's a mistake in the module handbook. It comes from not being able to get practical when we want it to be. On the 11th of March, you're going to need to submit electronically a report on the practical and an essay on the subject of your choosing about the scientific advance of discovery. So that essay is going to be due on the 11th of March. I forgot to move the date from the that was originally planned when I put the practical was going to fall off. Yeah. And at the end of the module, you will have an in-class test which will look at reading of a scientific paper. So we'll be asked questions on paper, and at the end of the module, you're also going to start to get some lectures on how to interpret and present data, and you'll have a test, and that will also be part of your test. So the test at the end of the module in the week starting the 1st of April, and an electronic submission will be due on the 11th of March. Okay?
Just to say something about the essay, we're going to give you some lists of suggested topics, but you're not restricted to that list. So those of you who already know or can decide what you want to write about, that's entirely up to you. Those of you who need a bit of guidance, I'll give you a timeline of some scientific milestones and breakthroughs, and you'll be able to pick one of them. You can pick topics from any of the sciences, so you're not restricted to the life sciences. And as you've seen so far, a great deal of the history of science is actually about things that today we would call physics or chemistry. But at the time we probably just thought of natural history and natural philosophy. And the reason why the history of physics and astronomy has been so important is that it gave us a lot of the approaches that we still use in science. We still use observation, we still use deduction, we still use inferences, we have certain things of evidence. So you're not restricted to only writing about the life sciences, and we'll give you a list of people and breakthroughs that you might take some inspiration from. You are asked in your first tutorial to tell the rest of your tutorial group what your essay topic is and why you've chosen it. So we want you to pick something and to know why you have picked it. So you could just pick something random from the list, but then in the tutorial, when you're asked why have you picked that, you're going to be put tongue-tied. So we do want you to think about the topic you've picked, and we want you to be excited about it. So we don't want you to pick something that doesn't interest you. And that will be very much the topic of your first tutorial. Justifying the rest of the class while you're taking it, and also discussing with your tutor ways of approaching the essays and researching them.
Yes. So one of the things, there are a couple of things we will tell you. Firstly, in the essay you're going to need to explain how the discovery or advance took place. And we say advance because we'll also be receptive to discoveries or technological things, so inventions. Certainly one of the main things that I might be inclined to go with is the Green Revolution as a plant scientist. And that's really not science at all. It's technology. It's how to achieve something. So that's okay as well. But whether it's science or technology, we want you to look at the underlying methodology as well. So how was it made? And we also want you to explain why it was important. And although we haven't decided quite how much yet, I will also give you a warning that there will be some marks allocated to the quality of the writing. So the quality of your written English will be an explicit, that there will be a percentage of marks will be allocated to that. Okay, we're looking for 1,500 words for the essay. I will say that the slides will go on Blackboard, but for the most part, until you've gathered, they're more of a roadmap than something you could work from directly. And we're also going to ask you to write up a 1,500-word report on the practical. We'll ask you to write that in the style of a short scientific paper. By that time, you should be starting to look at the two scientific papers, following on from the third tutorial. And one of the other reasons why it is going to be important that you attend the first tutorial, the second tutorial will be on the design for the practical, that might be the third, but to that in a moment. I'm going to give you a little demonstration first of what the practice is going to involve. Okay, so I'll try and bring this to the visualizer. Okay. Is it big? Okay. Okay. We see this? We've got two test tubes. And this is going to be the basis of your experiment. So we're going to take from this and add it to this. Can you tell me now what the reaction you're doing is? Recognize the purple colour? Should do. There's the right answer up there somewhere. If I tell you that starch is in one of the tubes. So it's the iodine starch reaction. But we're going to be doing it with a twist. Okay? So, again, we've got starch in this one, but watch what happens now. Watch it. Watch it. Okay. And so for a week of fun, what we're going to be doing is asking you to hit a time. So we're going to give you a time and say that we want you to work out a way of getting the tube to go at that particular moment. Now this one's got a different amount of, it's actually a score weight. Everyone know what a score weight is in day-to-day English? It's vitamin C. And you can do this as well. And this actually is another way you could plan on doing the experiment. You may have heard something slightly ominous in my phrasing so far. There we go. Gone. Gone. Back. Now, so what is actually going on is that what actually makes the starch colour is the binding of this triiodide anion into the middle of the starch structure. And usually you get this by using a mixture of iodine and iodide, so you can get formation of this. But in this reaction, we're doing it in a slightly different way. We're doing it by the addition of hydrogen peroxide, which catalyzes this conversion. So this generates the triiodide. Now, in one of the tubes, I had the hydrogen peroxide in starch. In the other, I had the potassium iodide, the I-, either water or ascorbic acid, so vitamin C. Now, the ascorbic acid grabs the triiodide and converts it back to iodide. So it mops it up, and so that's the reason why the colour disappears. And we will, I guess, give you some bonus marks that you can spin on to do some more experiments as well. For example, I might need to make sure that you have some lemons available. You might want to think about what you might do with lemons and some additional experiments. And there are some other things you can think about as well. Right, because the kick idea is that we will put on Blackboard what reagents you will have available, and you'll be able to ask us if you want more, and we'll say yes or no, but we aren't going to be giving you a schedule. You are going to have to design this experiment yourself. And so, if you just show up without having done any preparation, this is not going to be a good practice. You will have a tutorial where you'll be able to discuss with the member of staff what your plan is and how you are going to go about it. You need to be thinking a bit about the things you've been learning already in terms of standard curves and the like. So you will be given support in this, but it does mean that you are also going to need to form a group within your tutorial group to start to do the plan. Which is another reason why it's important to come along to the tutorial so you can arrange who you're going to be working with and exchange content. Okay, and as I say, we will give you a time, and you will need to work out a way of carrying out a set of experiments in the laboratory which will allow you to hit that time. And as I say, towards the end of the module, you'll have a test on the statistical stuff that Andrew Dalby will be coming in to give you in the lectures later on. And the other thing that's actually quite important is that we are noticing that in the second year, increasingly, when students are in their literature review and they start to do essays based on scientific literature in the second year, are increasingly finding that transition from working from textbooks to working from published scientific literature difficult. Now, we will be having lectures talking about the scientific community, what scientists do, how scientists work, what career path a scientist is. And we'll also be talking about how scientists talk to one another. That particularly involves what's called the scientific literature, the journals in which people publish their research findings. So we will be starting to introduce you to the scientific literature, how to find papers, how to read them in some of the sessions, and you'll be given a comprehension test as part of this test at the end of the module as well. Okay, so the idea is that we're starting to get you on top of how to do this type of reading earlier than we have done in the past. And we're going to be teaching it to you rather than just throwing you in at the deep end and expecting you to manage. Okay. I think that's where we're going to finish for now. So maybe give you a 15-minute break and we'll be starting. Data handling, essentially statistics without statistics. So I think we'll be covering Andrew Dalby's stuff. And that will be becoming more pertinent towards the end of the module. And the library is getting in quite a few more copies of that. The library is also getting in copies of this, though I'm thoroughly recommending anyway. Bill Bryson, a short history of nearly everything. It doesn't cover all of the stuff we've been talking about because it focuses on current thinking. And a fair number of the things we've been talking about are things that have subsequently been displaced or improved upon. But it's a very good book about science in general, and it's very entertaining. It's pretty much everything Bill Bryson has written is. And it also does talk about the evidence and the social context. So it brings together a number of things that we want you to be thinking about in terms of the model. So thoroughly recommended in most ways. Certainly not a bad thing to be looking at if you're looking for ideas for your essay. But we're going to carry on by asking you for some of your thoughts on any of the themes, examples we've talked about in the first part of the lecture. Nothing at all. What characterises what we've talked about?
The fact that everyone was first focusing on this thought experiment.
That's right. So we're looking at the thought experiment, and then we're moving towards a more empirical system where we're actually starting to go out and observe things. And that's important. And we'll come back to that one in a little bit. So that's one of the things to talk about. Anything else? That's excellent. We'll really be coming back to that next week. So what the lady here was saying is that you have the thought, there's an experiment to test your thoughts. So this is very good stuff indeed. And we will be touching on that in a moment.
Probably a moment to that we feel like think of something that we try to disprove it as much as possible.
That's it. That's another absolute. And that comes into the type of critical Okay, so, and what does that lead to?
Well, that's all leads to getting up in the right theory, what we know to be true.
I'm going to tell you that scientists never believe it. But, yes, you'll get, by being critical, we are incredibly finding nothing. Yes. And that very much connects in, as I said, to the reason why there are tools. Because you should be taking nothing for granted. Science is, I would say, almost unique as an endeavour, because we systematically attack our own ideas and get rid of the ones that aren't up to scratch. So you should, when we in lectures tell you stuff, be coming back and saying, how do you know that? What is the evidence? I don't believe it. Show me where that comes from. And as I said, that's systematically why we come to it. Because for one of us to stand at the front and say this is how it is intrinsically saying I am an authority. I am the one who knows everything, and I will be benign enough to pass it on to you. You should be creators of your own knowledge, and that means attacking us where we be.
And that's also
Well, not physically, obviously. Sorry.
There's also something to think about when you're reading a textbook. Far too many textbooks simply talk as though science is already the history of science. So they will tell you what is a cell, what's inside a cell, what a cell does. I had a very good biochemistry textbook when I was an undergraduate, which actually told me what the critical experiments were. There are very few textbooks like that. So if you're not happy with your textbook because it just tells you a list of factoids that you have to remember with no evidence for it, go and get another textbook. There aren't very many of them, but there are good textbooks that tell you, what the paper was, what the demonstration was. And it's too often it happens in science degrees that you're simply told the facts as though it didn't take 50 years to establish them. And most of the things, actually everything you hear in current lectures, everything you hear in cell biology, molecular biology, is still an area of ongoing research. What you get told in the lecture is the average picture about 5 years ago. Everything, if we were to tell you everything that's been published this week about molecular biology, you would never understand anything. So bear in mind, we're always going to get a simplified picture.
So this is very much the reason why I put in this quotation. Factual certainty is not what science is about. We're trying to get there, but it's a dynamic process where we're talking about changing and changing disruptively. We get rid of old ideas, we destroy the old ideas, and try and have something better, which in turn will be improved upon by this critical destructive process. And so, you should be getting into the habit of saying, how do we know that? What's the basis of it? What's the evidence? Looking at whether the experimental design is safe. Because we're starting to get those doing experimental design of your own. And is the interpretation correct? Is the interpretation reasonable? Is it the best interpretation? Is it the gloss that the person who's done the experiment wants you to take?
And one reason for asking what's the evidence is that quite often you're given two contradictory bits of information. When you come to do your literature review next year, one of the things you will find is, here's an abstract from a paper which claims one thing about cancer cells. Here's an abstract from another paper which contradicts the first one. How are you going to evaluate them? Are they both true? Are they both true under some circumstances? Or is one right and is one wrong? So knowing how to read a paper and decide what the evidence is something you will learn more and more about in this group, but this course is the beginning. If you're the kind of scientist that likes lots of facts, perhaps you should think always, what is the evidence for this?
A strange person in this context is Stephen Fry, who is some of the, if you look on QI, he's very besotted with science and scientific stuff. but he is clearly, he just reads the popular science books and spouts out whatever they happen to say. He doesn't show any evidence of really understanding how science works.
And now we come to one of our historical figures. And by the way, the people we're showing you aren't the only people who are important, but we're trying to find kind of a roadmap in relation to modern times, and necessarily we have to make a selection. We heard earlier about Bacon with his experimental method. Descartes, in some ways, is considered the mirror image, because Descartes is remembered for his emphasis on reason. So, experiment is thought by some people to be one kind of science, but thinking purely from reasoning is another kind. And both traditions are alive and well, and I would say that you have to have a blend of the two. Descartes lived at a time of wars and disputes, and a time when a lot of the Greek writers were being rediscovered in the West. And it seemed to Descartes that there was endless dispute about these old books, and these disputes were never resolved. And it seemed to him that a lot of scientific discussion was fruitless. He wanted to find a way of deciding whether something was correct or not. And his view was that whether something is correct or not depends on whether it leads to a useful outcome. You can't decide whether something is correct just because it comes from authority, like Plato or Aristotle. You have to say that the outcome of this discussion is that we can do something better. And Descartes asked himself, what's the only thing I can be sure of? What's the only thing I can be certain about? And he decided that the only thing he could be certain about was his own mind. And does anyone know the famous expression that's sometimes attributed to Descartes? You do, don't you? Because you're nodding. What did he say?
I can't pronounce it, but I think it's cogito ergo sum.
Yes, okay, that's the Latin. I think, therefore I am. So that was Descartes' famous expression, I think, therefore I am. He couldn't be certain of anything else. He certainly couldn't be sure of an experiment because our senses might be unreliable. He couldn't be sure of his own sensations because our bodies sometimes trick us. But the only thing we can be sure of, he thought, was our own minds, our own thinking. And so Descartes was an extreme example, if you like, of the kind of scientist that relied on reason. So cogito ergo sum. I think therefore I am. This was actually a milestone in the history of science because it in a way separates human beings from the rest of nature. So if the distinctive thing about human beings is that they think, then somehow they're not really part of nature anymore. And this is quite a new idea in the Western tradition. Human beings haven't really seen themselves as radically different from the rest of nature. Humans, birds, animals, trees. We were all part of God's creation in a sense. But Descartes thought there was something special about the human mind and also its ability to plan and to operate on the world. So he's still remembered for that particular insight. And this view that mind is different from the rest of the world is sometimes called dualism.
I should say at this point that we are still endorsing it as a view, but it does come quite usefully into the scientific method because of this idea that you can function as a detached observer with an objective view from outside what you're observing. This is one of the reasons why we place this emphasis on writing in the passive third person. So you don't say, I did this in the experiment, you say, this was before. So an important idea in philosophy, not necessarily in science, other than the way that we approach our observations, this idea that we can be outside the observation.
contribution to the way we think about physics, because at this time in the West we'd inherited Aristotle's idea that the world can be thought of as being made up of hot and cold humours. The idea of the humour strikes us as very strange now, but the Greek humours were very influential in thinking. And so people would say that if you were ill, for example, you had too much of one kind of humour. Descartes thought humours were nonsense. He said you can't think about physical stuff as if it was made up of qualities. It has to be made up of quantities. And he was one of the first people to try and put physics on a mathematical basis. He said the only thing I know about this book is that it's got a size and a shape and a depth. And so maybe we should base all the physics on quantities like size and shape and weight. We shouldn't be thinking of the book as being a blend of hot and cold. Quite a novel idea at the time, but as you know, that's the one that we now hold today. So, as well as his contribution to, if you like, method, the objective way of looking at the world, he also proposed a program for thinking about physics. So this is the idea of Cartesian doubt. So he wasn't going to accept anything. There's going to be no received opinion, and he was only going to accept things that he was sure of himself. And the first thing he was most sure of was his own knowledge. And so we come to stories like this. And this was in the papers a few weeks ago, both Stuart and I spotted it and laughed. This is the kind of rubbish you read all the time. Fizzy drinks and depression. And we can laugh at it, but there are people who think, well, it must be true, it's in the papers, and you're allowed to print things that weren't true. Quite often an authority is cited. You're all familiar with stories that say scientists at the University of Cambridge have proved, or big breakthrough in cancer reported by Harvard. And very often the story is something else when you pursue it. And this whole thing about fizzy drinks linked to depression. Well, actually the clue is in the wording, isn't it? Because linked is one of those words you want to look out for when you're reading newspapers. Anything that is linked is almost certainly not proved. This is going to be some association between depressed people and having fizzy drinks. Why might depressed people drink fizzy drinks?
Particularly diet fizzy drinks. The claim is actually that it is low-calorie fizzy drinks for profit.
So low-calorie fizzy drinks are linked to depression. The paper perhaps wants you to think that low-calorie fizzy drinks cause depression. Link and cause are not the same thing. But it's very easy to fall into the trap of thinking that they are.
Just to clarify, what they actually did was they took a large number of people, 250,000 people, asked them how they felt, and asked them how much low-calorie fizzy drink they consumed. Can you see the problem with this design? The example that really amuses me in this case is apparently there is an extremely strong link in this country between consumption of ice cream and death by drowning. Anyone tell me why? Where do you drown? Seaside? Where do you eat ice cream? Why?
And the world is full of associations like that. As I get older, the national debt goes up. But it's not because I'm getting older that the national debt is going up. And it's also not the national debt rising that makes me get older. So, it's easy to make a link between things that is not in any way causal. Which is something that the papers overlook. Maybe the person who wrote this knew that and was just having some fun, but you sometimes think, reading even the serious papers, that that journalists are confused. They think everything that comes out of the lab proves causation.
should say in here that the link to the BBC coverage is much better.
That's why we pay license fees, isn't it? Okay, so again back to data. So if his objection to experiments and also to anything you perceive with your senses is that they can deceive you, how can you really believe what you are looking at? On the other hand, he believed that the mind was the one thing that you could discipline from. Now, plainly you can't live completely inside your mind, and Descartes himself did actually do experimental science. But he wanted to make a claim for, if you like, the uniqueness of the human mind as a way of working out problems. And he believed it's possible to solve a lot of things just by pure reason before jumping into a lab and doing an experiment.
Okay, now we did actually, the first time this slide came up, pull up one of the other points that we were looking at, which is that we're seeing ideas displaced by better ideas, we think. So again, we're going to be developing from that. Now, we spoke in the first part about how the Copernican system came to replace the Ptolemaic system. The Ptolemaic system is the 3rd century. Now, at the time, it could actually be said that both models were consistent with the available evidence. So why might we actually prefer the heliocentric system to the Ptolemaic system, the Earth-centered system? Why would you decide one over the other? Any thoughts on that?
Is it because from studies done by people like Kepler, Brahe, and Isaac Newton proved that that system is
That's right. You've got the exact right names there. Brahe, who produced, he was actually the person who produced the observations. He was very careful numbers, and then Kepler worked from those numbers. Now Kepler is another example of somebody who is an extremely good scientist. He came into the work and he went to Brahe to look at his data because he had an idea that there were 7 mathematical solids, so tetrahedron, cube, octahedron, and so on, and 7 planets, and that these must be connected. So what he was looking for was a mathematical connection between the perfect solids and the orbits of the planets. And with the utmost reluctance, he, after a long time looking at data, he found that it was not so. And I will jump on a bit and then come back. So if we come on, what he actually found was that in fact the planets moved in ellipses by small. What happened? Oh, I see. Sorry, I didn't hear that. So Kepler came to this law of ellipses, but you're quite right. The person who eventually seconded matter was Newton with his law of gravitation. Now, this is arguably the point at which modern science, not just in the law of gravitation, but the laws of motion, come into being. Because this is the point where we start to have the idea that there are universal laws that describe things well enough that we can make predictions. And let's say this starts to come through in Newton's great book, The Principia, which I think very few people have read, and indeed he systematically made it difficult to read. Newton was an extraordinary chap. He was obsessed with all sorts of things. The first scientific laboratory at Cambridge, and was prone to do things like, apparently he stuck a sort of blunt needle around the outside of his eye to see what would happen. Not into the eye itself, but sort of probe around the eye socket and see what was there. And he still seemed to be able to see afterwards, but I wouldn't necessarily recommend doing it yourself. This is one of the famous representations of Newton by William Blake. It's been reproduced in this form in front of the British Library. But the thing that people often don't seem to know is that Blake was satirising him. That the point here is actually that Newton is carrying out these mathematical calculations on the paper in front of him, and that he is ignoring the movement, the actual movement of the heavens above. So Blake had some idea that Newton, by his focus on these laws, these underlying principles, was ignoring the mass of reality and was therefore useless. That's not, however, there's this idea that we can capture what is going on and describe it. I say particularly describe it in a predictive way. It is really where modern science takes off. So I think we would go with Newton rather than with Blake. Blake is a wonderful artist and poet. The Dark Satanic Mills in Jerusalem were actually said to be reflecting Newton's vision of the universe as a mathematically describable system, rather than is often thought the scenes of the Industrial Revolution. And Newton is also, this is a quotation you often see of Newton, if I have seen further, it is by standing on the shoulders of giants. And again, this is kind of taken out of context. It's usually used as indicating that Newton was this sort of great and magnificent person, but in fact, it was a quite pointed attack on this person, Robert Hooke, who was one of his rivals, another physicist and scientist at the time. We'll be talking about what he did achieve in a moment, but Hooke was notoriously short. So by saying, by standing on the shoulders of giants, he was saying, certainly not Hooke. But Hooke does connect into the way that the Principia came into existence. Because there was a bet between Sir Christopher Wren, the architect, who was responsible for St Paul's Cathedral, amongst other things in London, and was also a scientist, historian in his own right. Hooke and Hawley, who's famous for the comet that he didn't discover, he worked out that it was the same comet that kept coming back. So he worked out its orbit and then predicted the return, rather than actually discovering it himself. And they had a bet based on the slide we jumped onto before, which is the ellipse. So Kepler had worked out that planets seem to be moving in ellipses, and they had a bet as to who could discover why. Now Hooke said he had already worked it out, but he didn't want to spoil the challenge for the others, so he wouldn't tell them. Whether he did or not is not known. But what then happened is Hawley dropped in on Newton, and we have this description of the exchange. Dr. Hawley came to visit at Cambridge, and after they had some time together, the doctor asked him what he thought the curve would be that would be described by the planets. So this is the force of attraction towards the sun, you sit to the square of their distance from it. This is Hawley asking Newton. And Sir Isaac replied immediately that it would be an ellipse. The doctor, as Hawley, struck with joy and amazement, asked him how he knew it. Why, said he, I have calculated it. Whereupon Dr. Hawley asked him for his calculation without further delay. And Sir Isaac looked among his papers but could not find it. So he made this huge discovery and lost it. It's obviously something like mine. Though with, I imagine, rather more quality in it. And so this set off the exchange, which culminated in Hawley pushing for the Royal Society to publish the Principia. This is one of the elements in it, Newton's law of gravity, which then goes on to predictively describe how the planets move in ellipses. Newton's laws of gravity and of motion were sufficient to be good to be used in the calculations for the lunar landings, are still, to some degree, have been superseded by Einstein, but for most practical purposes, these are still incredibly powerful predictive tools to this day. And so this is again an element, an important element we'll be coming back to next week. It is one thing to observe and produce a description of what you have observed, to be able to abstract a general principle from those observations and say, okay, if I am right, then this will happen, is a step further. Of course, that's what we're going to be asking you to do in your practice. We're going to ask you to come up with a description of what determines the time between the addition and exclusion and the appearance of the colour, and then use that to say, okay, therefore I would be able to make the colour appear at this time by adding these quantities real units. Okay. And again, we've already touched upon the interconnections between different sciences. How optics led to the creation of the telescope, which then leads to Galileo's discovery. Optics also leads into another critical discovery of greater importance to us as biologists. Next slide.
And that is the microscope. And what you can see here is the microscope that Robert Hooke didn't build for himself, the one that he used. And this is currently in a museum in the United States. I know the United States is huge, and I don't know which museum it's in, I'm afraid I don't. But I think it's a beautiful object, and you can see it's accompanied by these little, this glass globe and a prism to illuminate the specimen, which will be held in the chamber down there. The microscope had been invented around 1590 in the Netherlands by some Dutch makers of glasses, spectacles. And for a long time, it was just seen as a kind of curious toy. You could use the microscope and you could look at things with it and you could magnify them. It doesn't seem to have been until about 1640 that people started looking at biological specimens with the microscope. In fact, there's an Italian publication from the 1640s that looked at the compound eye of the fly. And, I mean, we can only imagine kind of how much interest there would have been at the time. You know, the first time anyone had a microscope to look at things, you'd use it to look at everything, didn't you? And the telescope was the same. Galileo pointed his telescope at everything in the sky to see what was behind that. And Hooke published this book called Micrographia, which does actually contain telescope images as well, but what's remembered from it is his micrographs, his drawings of objects he looked at. And this book was a bestseller in his day. And he's remembered for his very careful drawings of, this is actually a flea, but I mean, as anatomical drawings, it's pretty good. I mean, he's getting what's easily called the coccyx and the little bristles on them. He's got, you know, features of the mandibles and the proboscis. That's a very careful drawing, so very carefully observed under the microscope. He also drew this picture of cork. This is the bark from a cork tree. And it very clearly shows the individual cells. Cells have been noticed before in plant material, but it's probably Hooke's book that popularised the idea that biological substances are made up of cells. He also seems to have looked at fossilised material and proposed that little inclusions that he could see were extinct organisms. He was very troubled by this idea because at the time, of course, there was no widespread idea that organisms might once have lived and are now extinct. That didn't seem to be part of anyone's plan. It certainly wasn't in the Bible, and that was a serious thing to worry about if you're a scientist living in Europe. But seems to have some idea that there were once animals on the planet that aren't here anymore. It was one of the very first suggestions of extinction. So that was Robert Cook with his micrographic.
I mean, I think that this looks quite a dull picture, certainly compared to the movie. But I think you cannot underestimate the importance of this in biology, because it shifts our emphasis to, it starts the route from which we're looking at organisms primarily as something that exists on a big level, to looking at how the individual bits of them are working. And that's something that, as Jeffrey and I were discussing yesterday, that is business that we're still ongoing. The idea that if you are ill, it can be caused by a single cell infecting you, the idea that things can be going wrong, not on the organ level, but on the level of individual cells, is a profound shift in the way we think about cells. This is something called a paradigm shift that we need to come back to next time. Okay, so this is our summary of where we think the module is going. Talking about why this is important. So to be a scientist, it isn't just a matter of learning science. You have to be, it's a matter of being a professional practitioner. You need to be able to design and carry out your own experiments or other pieces of research. You need to be able to interpret that data rigorously and critically. So think about all of the possible ways you can interpret it, and to evaluate other information you get. To look even at scientific papers that are being peer reviewed by other scientists and say, okay, that it sounds okay, but named Cavendish, whose papers were gone over long after his death by the very famous physicist James Maxwell. And he found that he had discovered lots and lots of things. And pretty much all of it had subsequently been rediscovered by someone else, and now had